We ended our class the other day talking about the t-star and how to find a good t-star value. Let's look at this one example before we move on. This wants us to construct a 99% confidence interval for a sample size of 75, and we're looking for our t-star value. So that means our degrees of freedom would be equal to 74. And I can either use my calculator, and if I use my calculator, that's inverse t, and I'm going to type in 0.995. And the reason I'm going to type in 0.995, remember, is because we would want the middle 99%, which means this right here would be a 0.5%, and right here is a 0.5%. And so from this high boundary down would be 0.995. Okay, then I have to enter in my degrees of freedom, which is 74. And that's going to give me a value. That's going to give me a value of 2.64. Okay, here's the big thing to notice here. If I use table B, I notice that my degrees of freedom options go from 60 to 80. Okay, if I choose 80, that's a sample size larger than what I actually have, which is going to make my interval smaller than what it actually should be. Okay, which may means I get a wrong answer. Okay, if I shorten the interval, it may not include the real mean that I need it to include. So we always want to be more conservative and go with the smaller degrees of freedom. And if I look at table B and I use 60, I would get a t-star value of 2.66, which is going to make my interval just a little bit wider. Okay, so one thing to know is always make sure you tell them whether or not you're using the calculator or using table B, because the difference in the answers could be a result of which one you use. Okay, so let's talk about the actual formula for a confidence interval for means. Remember that the formula from the formula sheet is the statistic, which in this case is x bar, plus or minus the critical value, which is t star, times the standard deviation of the statistic. Well, we've already talked about how we don't know the standard deviation of the population, so I have to plug in s of x over square root of n here. That would be the standard deviation. Okay, remember that when we substitute sample data in for population data, when we talk about standard deviation, it actually is standard error. So this is the formula for standard error of the sample mean. Okay, to interpret this, basically it's the same thing as standard deviation. On average, how far away from our population mean is the sample mean that we have? Okay, this standard error is not on the formula sheet. But remember, the formula sheet does give you the standard deviation of x bar, which is this. And so all you need to remember is that if I don't have the population standard deviation, I just need to plug in the sample standard deviation. Okay, so we already have the formula. Remember that this formula is also not on the formula sheet because it gives us the generic statistic plus or minus the critical value times the standard deviation of the statistic, all out in words. Okay, so all I need to be able to do is go from those words to these symbols, knowing whether or not am talking about mean or proportion. So, 3 conditions for constructing a confidence interval. 1, it's got to be random. 2, it's got to be normal. Hopefully these are beginning to look familiar. 3, it's got to be independent. Okay, random and independent, we find the same way that we did earlier. If it's random, it's going to say it in the problem, or give you something to go off of in the problem. And if it's independent, it's either independent or use the 10% condition if it's sampling without replacement. Okay, for normal, that's the one that's different. For normal, we're talking about means. So we're going to talk about the CLT, which remember the sample size has got to be at least 30, or it's got to come from a normal population. So those are our conditions. So let's look at this problem, and this problem actually is not the problem that I wanted to be in the notes. I noticed here that I have a serious typo, and I typed the same problem twice. So you can just ignore all of this right here and listen to me read the problem instead. The principal at a large high school claims that students spend at least 10 hours per week doing homework on average. So to investigate his claim, an AP statistics class selected a random sample of 250 students from their school and asked them how long they spent doing homework last week. The sample mean was 10.2 hours, and the sample standard deviation was 4.2 hours. Okay, so I'm going to talk us through a lot of this, simply because I just don't have enough room to write it. So the first thing is we would state. Okay, and to state, remember we need to talk about the parameter and the confidence level. So we would say we want to estimate mu, which is the mean time that students at this school spent doing homework in the last week, at the 95% confidence level. Okay, then we want to plan, which means we need to write down what we're going to use. If you want to use the name of this confidence interval, it is the one sample t interval for the population mean. So one sample t interval for mu. Okay, the other option is that you can say we want to use the formula x bar plus or minus t star times the standard deviation of the sample over the square root of n to calculate the interval, provided these conditions are true. First, random. I said that they took a random sample of 250 students, so it's definitely random. For normal, I see that their sample size is 250, which makes it greater than 30, so it's large enough to assume that it's normal using the central limit theorem. And then I need to do independent. Well, it says that they are at a large high school, so I can assume that there are 2,500, 250 times 10, students at this large high school. So then I'm ready for the do step when I plug all this in. 10.2 plus or minus, okay, I need to find the t-star value. So I need to say that my degrees of freedom is 250 minus 1, which is 249. And then I need to either use the calculator or I need to use table B. I prefer the calculator. So using the calculator, we would say that it is, and we would say inverse t, 0.975, comma 249, and I would get 1.97. So using the calculator, t star is equal to 1.97. Okay, so 1.97 times the standard deviation, which is 4.2, over the square root of 250. And remember, I can either plug this into my calculator or like as it is, or I can use my calculator. If I'm interested in using my calculator, I'm going to the test menu and I'm going to choose the option that says t-interval. Okay? And it'll give me two options. It'll give me an option for data or an option for stats. If I have information like this right here, I want to make sure I choose the stats option. If I have just raw data, then I would choose the data option. Okay, so I click stats option and I enter in the things that it asks for. And I get an interval from 9.68 to 10.72. And you can write it just like this. This is called interval notation. So then what I want to make sure that I do is I want to interpret it. And I want to say we are 95% confident that the interval from 9.68 to 10.72 hours captures the true mean time that students at this school spend doing homework in the last week. And then that would complete my 4-step process for this problem. Okay, let's talk a little bit more about T procedures. The T procedure is a pretty robust inference procedure. And what robust means is that it's fairly accurate even when a condition is violated. More often than not, we talk about the condition that's violated as being the normal condition. Okay, and I will tell you that the Z interval is not robust at all. If the normal condition is not met for the Z interval, we are not likely to get accurate results at all. However, the T interval is robust with respect to the normal condition. Okay, but we have to make sure that we follow some guidelines. And here's our guidelines. 1, always graph your sample data. To graph our sample data, I can use a few different graphs. 1, I can use a histogram if it's a really large set of data. If it's spread out over several, like 10s, 20s, 30s, etc., I could use a stem plot. But the one that I like to use the most is the dot plot. So those 3 options are all valid options for graphing my sample data. Okay, so here are our conditions. If the sample size is less than 15, then you need your data to appear close to normal, meaning that it needs to be roughly symmetric, have a single peak, and be no outliers. Okay, if I can see that it's skewed, or if I can see outliers, then I can't use a T interval. Okay, if my data is greater than or equal to 15, I can use it as long as it is not strongly skewed. Okay, so as long as it's not skewed crazy one way or the other, and as long as there are not any outliers, I can still use it. Okay, if n is greater than or equal to 30, then it doesn't matter if it's skewed or not. The central limit theorem allows me to use it. So those are the 3 levels that we have. For this one, okay, it's got to look approximately normal. For this one, it just can't be strongly skewed one way or the other. And this one, I can use it no matter what. Okay. These actually should have gone here. And the way to lose credit for the normal condition is by not graphing it. You must have a graph. And remember that this is only for means, because for proportions we use a Z interval, and so we have to use n times p and n times 1 minus p. And yes, you can use a calculator in a do step. Just make sure that you show all your work and be careful of how you punch things in. Alright, so finally let's look at this final example that actually gives us data. instead of statistics. So as part of their final project in AP Statistics, Christina and Rachel randomly selected 18 rolls of a generic brand of toilet paper to measure how well this brand could absorb water. To do this, they poured 1/4 of a cup of water onto a hard surface and counted how many squares it took to completely absorb the water. So here are the results. So here's their data. Construct and interpret a 99% confidence interval for mu equals the mean number of squares of generic toilet paper needed to absorb 1/4 of a cup of water. So, we want to estimate. Mu, which is the mean number of squares of generic toilet paper needed to absorb a 1/4 of cup of water at the 99% confidence level. Okay, so then I want to plan. And so for my plan, I say we will use X bar plus or minus T star times the standard deviation of the sample over the square root of n. So then I need to check my conditions. Random. They randomly selected the toilet paper. So it meets random. So they randomly selected the rolls of toilet paper. Okay, I can go ahead and check independent. We can assume there are more than 180 rolls of this generic toilet paper. Okay, then the final one is normal. And I want to make sure I graph my data. So I'm going to use, based off of what we have here, a dot plot. And I'm going to graph it up here just for the point of being able to see the data as I graph it. So I'm going to do a dot plot. And I'm going to start at 20 and go to 30. And I need to label it. Even if I don't label every one, I can label every other one. Oh, and I'm short one. And then I need to title it. Okay, this is the number of sheets. And so then we can get our dots. So I've got one at 29. Another at 29, 20, 24, 25, 27, 29, 28, 21, 21, 24, 25, 27, 26, 25, 22, 24, and 23. So there is my data. I can see that it's not really strongly skewed because since my sample size is 18, that's greater than 15, it would have to be strongly skewed or have outliers for me not to be able to use this. And it is actually neither. It doesn't seem to be strongly skewed, and it doesn't have any outliers. So I can say, so I can say that since it's normal, and I don't know where my independent just went, but since it's normal, because the data is not strongly skewed, we can assume the population distribution is approximately normal. Okay. Now for the do step. Okay, the first thing I'm going to do with the do step is find my degrees of freedom. So df is equal to 18 minus 1, which is 17. And then I'm going to say using the calculator, T star is equal to 2.898. Okay, then I have a problem. I need to be able to plug X bar and the standard deviation in, but because they gave me my data here, I don't know them. So I'm going to plug all of this into list 1. And once I have it all plugged into list 1, then I'm going to hit choose my T interval. So if I go choose my T interval, and then instead of hitting stats, I'm going to hit data. And I'm going to tell it to look in list 1. I'm going to make sure the frequency stays 1. I'm going to choose my confidence interval of 0.99. And it's actually going to give me my X bar of 24.94, my standard deviation of 2.86. So then I can plug that information into my interval. So 24.94 plus or minus 2.898 times 2.86 divided by the square root of 18. And it also gives me my interval. And this tells me that my interval is 22.99 to 26.897. So then I can interpret, and I can say we are 99% confident that the interval from 22.99 to 26.897 captures the actual mean number of squares of generic toilet paper needed to absorb a fourth a cup of water. And there you go. That's a full, we did one full problem when they gave us statistics and one full problem when they gave us data. And there you go. That's everything about Chapter 8.